So I don't believe in a God, right? However, I don't like the antagonism that occurs or is produced by this question. I mean, what you can say if you're a cosmologist, what you should say is, so we know that the universe was very hot and dense 13.8 billion years ago. We don't know how it got hot and dense. We don't even know, actually, if the universe had a beginning in time. Don't know. Essentially what happened before the Big Bang, right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation.
What existed before the Big Bang? This question has always been a challenge for scientists, but now it seems they've found the answer to it. But it has left scientists shocked as Brian Cox revealed that something terrifying existed before the Big Bang.
So the idea is the universe was there, in a sense, cold and empty, and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. We don't know why or how the universe got into the state that we call the Big Bang. We don't know whether the universe existed before that. We have theories that it did, theories called inflation. Before the universe was hot and dense, which we used to call the Big Bang, space and time is still there, and the universe is expanding extremely fast. It's called inflation. And then that period draws to a close, and that expansion sort of slows down and almost collapses and changes, and the energy that was driving the expansion gets sort of dumped into space and changes and ultimately makes the particles out of which we are made. So that's actually the standard model of cosmology now. So we do have an idea that we redefine the Big Bang as the hot Big Bang, and it's not the origin of the universe in time. It's the end of inflation. So we don't know whether the universe had a beginning in time, I would say is the correct statement as we are at the moment.
So, what existed before the Big Bang? Why has it left scientists terrified? Let's find out.
That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever, and it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, and then it slows down and stops in little patches, and each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse.
In the vast cosmos, the idea of absolute nothingness seems theoretical rather than real. Even if all energy were removed from the universe, it wouldn't be truly empty. Currently, the universe is full of matter, radiation, antimatter, neutrinos, dark matter, and dark energy. Even without energy, the universe still creates new forms of energy. This phenomenon confuses us. It seems the universe doesn't understand our concept of complete emptiness. If we removed all energy, leaving a void, one might expect the universe to reach absolute zero with no particles. Yes, that's not the case. Even in an empty universe, its expansion would still produce radiation. This extends far into the future or even back to the time before the hot Big Bang. The universe, it appears, never truly becomes void. Given all of this, is it plausible that the universe originated from nothing? We can be certain that something always persists. Even if particles, antiparticles, photons and quanta are removed, empty space remains. If we move away from any mass or energy sources, clear the space of external electric, magnetic and gravitational fields, and prevent photons or gravitational waves from entering, a kind of physical emptiness still exists in this space. Quantum fields endure, and the fundamental constants and laws of physics endure. There is an inherent, finite positive and non-zero value of zero-point energy in that space. This represents the closest approximation to nothing within our universe. While you might envision an even more nothing-like state, it lacks physical reality. No experiment can replicate such a condition. By adhering to scientific principles, we acknowledge that something always exists because true nothingness cannot coexist in our universe. Yet, the question of why remains unanswered by science. Presently, our universe appears far from empty. It's teeming with stars, gas, dust, galaxies, quasars, cosmic rays, and radiation from both starlight and the remnants of the Big Bang. With improved observational tools, we could potentially detect additional signals that we anticipate are present. This encompasses gravitational waves generated by any mass moving through a changing gravitational field, the mysterious signals from the constituents of dark matter, and a broader perspective on black holes, both active and dormant. Aside from those emitting the most radiation, everything we observe occurs in a universe that isn't static but is continuously changing. From a physical standpoint, it's intriguing to comprehend the evolution of our universe on a grand scale. The fabric of our universe, known as space-time, is expanding. This implies that if you position 2 points far apart in your space-time, the proper distance between those 2 points, the time it takes for light to traverse between them, and the wavelength of the light traveling from one point to the other all increase over time. The universe isn't just getting bigger, it's also getting colder as it expands. As light stretches to longer wavelengths, it moves towards lower energies and cooler temperatures. The universe was hotter in the past and will become even colder in the future. During this process, objects with mass or energy in the universe attract each other, forming clusters and creating a vast cosmic network. If you were to somehow remove everything, all matter, all radiation, every bit of energy, what would remain? Essentially, you'd have empty space itself, still expanding, still governed by the laws of physics, and still influenced by quantum fields that fill the universe. This is the closest physical approximation to true nothingness, yet it still adheres to specific physical principles. To a physicist in this reality, removing anything else would create an unrealistic state that no longer reflects the cosmos we inhabit. This suggests that dark energy as we currently understand it would still be present in this hypothetical universe devoid of matter. In essence, if every quantum field in the universe were set to its lowest energy state, we would arrive at the zero-point energy of space, where no additional energy could be extracted for mechanical work. In a universe containing dark energy, a cosmological constant, or the zero-point energy of quantum fields, it's plausible that the zero-point energy wouldn't be truly zero. As the universe continues to expand and cool, there will come a time in the distant future when radiation becomes the dominant component, surpassing other forms of matter and radiation, leaving dark energy as the primary influence. However, there's also a period in the universe's history, not in the future, but in the distant past, when something else besides matter and radiation held dominance. During cosmic inflation prior to the hot Big Bang, our universe underwent extremely rapid and constant expansion. Instead of being dominated by matter and radiation, the cosmos was controlled by the field energy of inflation, akin to today's dark energy, but much more potent and expanding at a significantly faster pace. If eternal inflation is accurate, but time remains finite, where might the universe have originated? There must have been a beginning, correct? To address this question thoroughly, let's unravel 3 commonly conflated concepts and discuss each individually. The hot Big Bang in relation to our universe, the theory of cosmic or cosmological inflation and its role in preceding and preparing for the Big Bang, and the issue of an ultimate beginning or origin for our universe, and why both inflation and the original concept of the Big Bang might not offer a satisfactory solution to this question. In the early 20th century, a significant synthesis took place when four key pieces of information came together. A breakthrough by Alexander Friedmann in Einstein's general relativity, showing that a universe filled uniformly with any form of matter and energy cannot remain static but must either expand or contract. The rate of this expansion or contraction depends on the overall energy density of space. Henrietta Leavitt's observational work established a connection between the period of brightness and dimness of variable stars and their inherent brightness, known as the period luminosity relation. Observations by Vesto Slipher measuring the shift in light, either red-shifted or blue-shifted, from our solar system's perspective in spiral and elliptical nebulae, which were later identified as galaxies, indicated that these galaxies were moving away from us at incredibly high speeds. Edwin Hubble, alongside Milton Humason, identified similar types of variable stars to those identified by Henrietta Leavitt in spiral and elliptical nebulae. This enabled them to gauge the distances to these galaxies and confirm they were beyond our own. These findings, combined with other data, led to the concept of the universe expanding. If the universe expands, it suggests that over time, space itself stretches, causing the matter within it to become less dense. As space expands, radiation like light waves not only becomes less concentrated but also stretches, leading to the universe cooling. If we rewind the clock, the opposite would occur to matter and radiation in the universe. In earlier times, when the universe was younger, it was denser and hotter. If we rewind further, all matter and radiation would have been squeezed into a smaller space, increasing the density of the universe. The light, which stretched due to cosmic expansion when we reverse time, would have had a shorter wavelength, resulting in hotter temperatures. If you envision going back as far as physics permits, you'd reach a singular state where all matter and radiation existed within a single point of infinite density and temperature. The initial idea of the Big Bang Theory resulted in the formation of 5 key expectations regarding the early universe's hot and dense conditions. These forecasts became the foundation of the Big Bang Theory. The universe ought to demonstrate expansion, as indicated by a distinct redshift distance relationship among extragalactic objects. Initially, the universe should have been relatively uniform, with structures like stars, galaxies, and clusters of galaxies gradually forming and evolving over time. In the past, the universe was hotter, preventing the formation of stable neutral atoms. This prediction led to the discovery of the cosmic microwave background, which is observable today. In the initial stages of the universe, when it was extremely hot, atomic nuclei couldn't form stably. This led to the creation of light elements such as hydrogen, helium, lithium, and their isotopes. The universe was so hot that neutrinos played a significant role. Recently, this prediction was confirmed, indicating that cosmic neutrinos should have detectable effects on both the large-scale structure and the leftover radiation from the Big Bang. With strong observational evidence supporting these predictions, the Big Bang Theory has remained uncontested as the primary explanation for the early universe since the mid-1960s, coinciding with the discovery of the cosmic microwave background. As evidence supporting the hot Big Bang Theory grew in the 1960s and 1970s, certain challenges surfaced that the Big Bang alone couldn't resolve. Several observations contradicted the concept of the universe originating from a singular state of incredibly high temperatures and densities. 3 of these challenges stand out. Firstly, there's the horizon problem. When we observe different directions, the universe seems to possess uniform temperatures and density throughout. However, since the onset of the hot Big Bang, these regions have never had the opportunity to communicate, exchange information, or achieve thermal equilibrium with one another. This raises the question, how did they evolve to exhibit uniform temperature and conditions across the board? Next, let's consider the issue of flatness. In a universe that's expanding, there's a continual tug-of-war between the initial expansion pushing things apart and gravitational forces attempting to pull everything back together. Remarkably, in our universe, these opposing forces appear to be perfectly balanced, resulting in a spatially flat universe. The question arises, why did our universe come into existence with these particular characteristics? Moving on, we encounter the monopole or ancient relic dilemma. If the universe underwent extreme temperatures and energy conditions in its early stages, why do we not observe any exotic remnants, such as right-handed neutrinos and magnetic monopoles? Theoretically, these particles should be detectable and still present today. Rather than just taking these conditions as how the universe came to be, which contradicts the scientific method, scientists are looking for a mechanism that would establish and arrange these initial conditions. Alan Guth introduced a solution to these cosmological mysteries in 1980 with a groundbreaking paper. He suggested that an early phase of rapid and continuous expansion, where the universe's energy wasn't spread among matter and radiation particles, but was an intrinsic part of space itself via a field or another mechanism, could solve all three issues regarding the horizon problem. The uniformity of temperature and density throughout the universe is attributed to the past interconnectedness of everything. This connection stretched during the early expansion phase called inflation, resulting in the current conditions observed for the flatness problem. Inflation expanded the universe so much that, regardless of its initial state, the visible part now appears uniformly flat. As for the monopole problem, the absence of ancient remnants is explained by inflation preventing the universe from reaching excessively high energies or temperatures. The maximum temperature reached after inflation avoids the formation of these remnants. Inflation not only explains these phenomena, but also presents a compelling alternative to the standard hot Big Bang model. Additionally, a further issue was addressed to demonstrate how a uniform and isotropic early universe could be reinstated after inflation. It became evident that inflation could act as a quantum mechanism for seeding the universe with initial imperfections or the origins of cosmic structure, ultimately leading to the intricate formations we see today. In the 1980s, inflation theory made precise and testable forecasts about the beginnings of cosmic structure that should be detectable in both the cosmic microwave background and the large-scale layout of the universe. These forecasts, crafted decades ago, have been validated by observations spanning from the 1990s to the present day, encompassing an almost, though not entirely, scale-invariant spectrum of imperfections, variations in density and temperature, density irregularities that are entirely adiabatic and not at all isocurvature in essence, fluctuations on scales larger than what a signal traveling at the speed of light in an expanding universe could generate, and a maximum temperature limit for the universe during the hot Big Bang, notably smaller than the Planck scale. Because inflation involves a rapid expansion of space rather than culminating in a singularity like the original model for the Big Bang, it presents an alternative depiction of the beginning. Instead of time and space gradually emerging from a single state, inflation proposes a rapid expansion leading to the Big Bang. This raises a fundamental question about the actual beginning of the universe, if such a notion even makes sense within the framework of the hot Big Bang. Without inflation, we could trace back and reach a singular state where the universe's size approaches zero in a finite time. However, inflation complicates this scenario. Its exponential growth makes it challenging to trace back to a singularity size, since reaching a state where the universe had zero size would require an infinite amount of time due to the exponential nature of inflation. Adding to the complexity, the observable evidence for inflation, such as quantum fluctuations leaving imprints on our visible universe, corresponds to just the final 10 to the power of 32 seconds before inflation leads to the hot Big Bang. If we were hoping to delay the start of an earlier grand event, inflation ruins those hopes. There's nothing observable that gives us clues about what, if anything, caused inflation. A fascinating aspect of inflation is called eternal inflation. When exploring how inflation works, almost any model that effectively addresses the issues with the original Big Bang and creates the necessary quantum effects to initiate the universe with imperfections will result in a scenario where, while inflation ends in certain areas like our own, there will be countless more surrounding regions where inflation continues, creating more space that keeps expanding. Essentially, once inflation starts, it wipes out any information about what existed before, and the inflationary state will persist indefinitely into the future. At times, quantum fluctuations, akin to those shaping the universe's structure, cause certain areas where inflation ceases, resulting in a hot Big Bang. However, these regions are far fewer compared to those where inflation persists indefinitely. Notably, no two separate regions with Big Bangs will ever overlap because the expanding universe drives them apart. Despite its appeal, eternal inflation has limitations. It's eternal only into the future, not into the past. In fact, it's been demonstrated that inflationary spacetime doesn't extend into the past infinitely and must have originated from a prior, non-inflationary, and possibly singular state. The issue of past time-like incompleteness can't be avoided by considering alternatives like bouncing cosmologies or cyclic cosmologies, as they face similar challenges. However, this doesn't necessarily imply that the universe originated from a singularity. While it could have, it's not a strict necessity. For example, one can envision a spacetime resembling the past, where inflation takes place by modeling the universe's expansion rate through a scale factor composed of a growing exponential plus a constant, rather than just a pure growing exponential. In essence, the hot Big Bang, while our most accurate model of the early universe, wasn't its absolute genesis. There's a limit on how far back we can extrapolate the temperature and density of our matter and radiation-filled universe. Prior to the hot Big Bang, there existed a period of cosmic inflation which initiated and led to the hot Big Bang. During inflation, space was saturated with energy, devoid of matter and radiation, and expanded exponentially. However, inflation couldn't have persisted indefinitely and must have emerged from some pre-existing non-inflationary state. Unfortunately, our knowledge of this earlier state is limited aside from knowing many things it couldn't have been. We don't live in a universe where matter drifts in empty space. We live in a universe filled with energy fields that interact to form everything we see. When considering the vastness of emptiness, the endless void, and mortality, it's striking how the idea of nothingness can provoke such fear. Did William Shatner, at 90, go on a space journey expecting to find the universe's mysteries, only to realize there was no mystery or grandeur? He encountered only death, witnessing a cold, dark, black void unlike any darkness on Earth. It was overwhelming and all-encompassing. Yet, in another paradox of nothingness, Shatner wasn't truly observing a void. Rather, he was looking at a vacuum where a lot was happening that he couldn't see. Quantum field theory is one of the most accurate theories in physics, known for predicting the outcomes of many experiments. According to this theory, the universe is not made of matter floating in empty space, but of energy fields that permeate space and interact, creating everything we observe, including ourselves. Some physicists describe these fields as fluid-like, similar to water in a pool, while others compare them to a room filled with varying levels of energy, like a field of distributed heat. These fields are constantly moving due to quantum fluctuations, brief changes in energy similar to ripples in a wave caused by external forces exciting the particles within the field. For example, an electromagnet can cause changes in an electromagnetic field. Even in their lower state, known as the vacuum state, fields remain active. Pairs of positive and negative particles continuously borrow energy from the vacuum, briefly appear, and then disappear, returning the energy. These temporary entities are called virtual particles. When the field is excited or at a higher energy level, it has ripples or waves that produce elementary particles that persist and interact with each other, forming the world we know. The type of particles created depends on the field. Different matter particles are associated with specific types of fermions, such as electrons, up quarks, down quarks, and neutrinos, which are fundamental components of all atoms. These fermions interact through three types of field: electromagnetism involving photons, the strong nuclear force involving gluons, and the weak nuclear force involving W and Z bosons. According to Cambridge theoretical physicist David Tong, without these force fields, matter particles would drift aimlessly in the universe without interactions or interesting behaviors. Then there's the Higgs field, which Tong compares to molasses spread throughout the universe. The Higgs field gives mass to other particles, stopping them from moving at the speed of light. Tong notes that this comparison is not perfect because it suggests friction, while in reality, different particles interact with the Higgs field in various ways. All fields, including matter and force fields, exist everywhere but interact differently. Some particles in these fields ignore each other, while others interact, leading to reactions and complex structures. The collaboration of these fields covers everything we understand and observe, along with much that remains unknown and beyond our perception. Oddly, the creation of matter particles is an exception. For instance, an atom forms when there's enough energy in the quark fields to produce quarks that aren't destroyed by antimatter quarks. Though the reason for this is not fully understood, gluons, which are particles related to the strong force, bind with two up quarks and one down quark to form a proton. Gluons then connect protons with neutrons to create a nucleus. Physicists proposed that the visible universe consists of remnants that survive the constant creation and destruction of virtual particles. However, the particles making up dark matter are a different issue. Although the universe is full of virtual particles, it doesn't completely negate the idea of nothingness. First, there's the nothingness before the Big Bang, which we don't yet understand. Additionally, this nothingness made up of vast fields of quantum energy seems to produce matter and force, leading to the creation of our world. Physicists are still unsure why some elemental particles persisted after the Big Bang. In his book, A Universe from Nothing, Lawrence Krauss, a theoretical physicist and cosmologist, argued that the evidence holds the answer. The inherently unstable nature of nothingness produces elementary particles. There's also the idea that the entire universe might be a large virtual particle. The vacuum genesis hypothesis proposes that the universe began as a large fluctuation in the nothingness that preceded it. Although this hasn't been proven, it's an intriguing concept. Ultimately, everything, you, me, the whole universe, amounts to a big bunch of nothingness. Even if you can picture an empty universe, this doesn't match reality. Adhering to the laws of physics is enough to dismiss the idea of a truly empty universe. As long as there is energy within it, even the zero-point energy of the quantum vacuum, there will always be some form of radiation that can't be eliminated. The universe has never been completely empty, and as long as dark energy exists, it never will be. The universe is the way it is, and while we try to understand it as much as we can, we should remain humble in the face of its vast unknowns. My only advice is to embrace the curiosity that drives us to explore, question, and uncover its mysteries. What if the universe we live in isn't the first one to exist? What if time itself didn't begin with the Big Bang, but simply reset? For decades, scientists believe that everything, space, time, and matter, started from that single explosive moment. But new research suggests something far stranger might have happened before it all began. And now, Brian Cox has stepped forward with a theory that could completely change how we think about the universe. Keep watching as we uncover what Professor Brian Cox just revealed about what might exist before the Big Bang. Let's start with what we know for sure. The Big Bang represents time zero, the starting point of everything. In a single instant, all space, time, matter, and energy emerged from a singularity, a point of infinite density. Within the first fraction of a second, the universe experienced an intense phase called inflation, expanding faster than the speed of light in an already expanding space. This event laid the foundation for everything that followed. About 1 second after the Big Bang, the universe existed as a hot, dense soup of particles. Within minutes, the first light elements formed through a process known as primordial nucleosynthesis. At that time, the universe was so hot and packed with energy that atoms couldn't form. Light, or photons, constantly collided with free electrons, preventing it from traveling any distance. For hundreds of thousands of years, the universe was cloudy and opaque. As it continued to expand, it began to cool. Roughly 380,000 years after the Big Bang, temperature dropped enough for electrons to combine with nuclei to form neutral atoms, an event known as the Epoch of Recombination. This changed everything. For the first time, light could move freely through space. The cosmic fog lifted, and light spread across the universe. The same ancient light still surrounds us today as a faint glow visible from every direction, stretched over billions of years into the microwave range. It's called the Cosmic Microwave Background, or CMB, essentially a photograph of the universe as a baby. By observing the CMB, scientists can see the universe as it appeared when it was only 380,000 years old, a newborn compared to its current 13.8 billion year age. This is the oldest light ever observed, a remnant of the Big Bang itself. Discovered in the 1960s, the CMB has been studied in increasing detail using satellites and advanced telescopes. It holds a massive amount of information. The tiny variations in temperature seen across the sky aren't random. They contain the first clues about how matter was distributed in the early universe. Slightly denser areas eventually collapsed under gravity to form galaxies and clusters. The CMB is, in essence, a blueprint of cosmic structure. It shows the tiny peaks and valleys that shape the distribution of matter and provides valuable insights into the universe's composition and geometry. After decades of analysis, scientists have determined that ordinary matter, everything that makes up stars, planets, and life, accounts for only about 5% of the total content of the cosmos. The remaining portion is far more mysterious. Around 27% is dark matter, and roughly 68% is dark energy. These values come directly from precise measurements of the CMB's features. New studies continue to refine this understanding. In March 2025, researchers from the Atacama Cosmology Telescope, ACT, and Princeton University unveiled the most detailed images of the CMB ever captured, 5 times clearer than the previous full sky map made by the Planck satellite. The ACT team even measured the polarization of this ancient light, the way its waves are oriented. This data reveals how much matter moved across different regions of the young universe. Before, we could see where things were. Now we can also see how they were moving, explained Dr. Suzanne Staggs, ACT's director. These images show subtle differences in density and motion within the early gas clouds, the fine details that shape the structure of today's cosmos. Such findings help scientists understand how the universe evolved from a simple state into one filled with galaxies, stars, and planets. By measuring light that has traveled for more than 13 billion years, we can literally see back to a time when the universe was only a few hours old, in cosmic terms. If the CMB represents the afterglow of the universe's infancy, what happened next? After recombination, the universe entered what scientists call the cosmic dark ages. The fog had cleared, but no new light appeared yet because stars had not formed. This darkness lasted until the first generation of stars came to life, likely between 100 and 200 million years after the Big Bang. These earlier stars, known as population 3 stars, were massive and short-lived. They ignited the darkness and began shaping the young universe. Forming inside clouds of gas that would later become galaxies, they marked the beginning of star and galaxy formation, a period astronomers call the Cosmic Dawn, when light first illuminated the universe. Today, for the first time in history, we're beginning to observe that era. The James Webb Space Telescope, JWST, launched in 2021, was designed specifically to detect the faint infrared light from extremely distant galaxies. Because light from the early universe has stretched or redshifted into the infrared spectrum, Webb's instruments are perfectly suited to capture it. In just its first few years, JWST has broken records, finding galaxies that existed only a few 100 million years after the Big Bang. One of these galaxies, named MAMZ14, was identified in 2025 as the most distant galaxy ever observed. The light we see from it began its journey just 280 million years after the Big Bang. In other words, we're seeing this galaxy as it appeared when the universe was only about 2% of its current age. The light from that era traveled nearly 13.5 billion years before finally reaching us, and JWST's instruments have now captured it. Since beginning operations in 2022, the James Webb Space Telescope has identified more bright early galaxies than scientists initially predicted. This unexpected abundance has excited researchers and raised new questions about how galaxies formed within the first 500 million years of cosmic history. Each newly discovered high redshift galaxy adds a piece to the larger picture, helping us understand how the universe's structure began to take shape. Take the MAZ14 galaxy, for example. Observations show that it was experiencing a rapid burst of star formation at the time it was seen. Its chemical makeup, containing more nitrogen compared to carbon, is similar to that of ancient globular star clusters found in our Milky Way. This indicates that even during this very early era, star formation may have worked differently than it does today. These findings are forcing astronomers to rethink their ideas about how quickly the small fluctuations seen in the cosmic microwave background could have evolved into fully formed galaxies. How could such large, bright galaxies appear so fast? Were stars and galaxies forming more efficiently than our models predict? Or is there something missing in our understanding of the universe's timeline? With new observatories being developed, scientists expect to peer even closer to the Big Bang, possibly detecting objects from the era of the very first stars. However, no matter how advanced our telescopes become, they'll never be able to show us what happened before the Big Bang itself. For that, scientists must rely on theoretical models. Over billions of years, gravity caused matter to clump together, forming a vast cosmic web. Galaxies are not spread evenly throughout space, they form along filaments and sheets, with enormous empty regions between them. This web-like arrangement traces back to the original fluctuations seen in the cosmic microwave background. Our cosmological models, based on the Big Bang theory and an expanding universe containing dark matter, predict that there should be an upper limit to the size of these large-scale structures. A key concept in modern cosmology, known as the cosmological principle, states that on very large scales, the universe should appear roughly uniform, without any single region being dominated by massive clusters or distinct patterns. When averaged across hundreds of millions of light years, every part of the universe should look nearly the same. According to standard theory, the largest connected structures that can form should be about 1 billion light years across. That's why astronomers were astonished to find structures that far exceed those dimensions. In 2024, researchers discovered a huge ring-shaped pattern of galaxies and galaxy clusters, which they named the Big Ring. It stretches about 1.3 billion light-years in diameter and roughly 4 billion light-years in circumference. We're seeing this structure as it existed around 9.2 billion years ago. That's how long its light has taken to reach us. Interestingly, it's located near another enormous feature called the Giant Arc, which spans an incredible 3.3 billion light-years. To give some perspective, the Milky Way's own supercluster measures only about 0.5 billion light-years across. Compared to that, the Big Ring and the Giant Arc are true giants in the cosmic landscape. Detailed analysis even suggests that the Big Ring may not be a perfect ring at all. It could actually be a spiral or corkscrew shape, twisting through space. If we could somehow see it with the naked eye, which we obviously can't because of its distance and faintness, one researcher said it would appear about 15 times wider than the full moon in our night sky. This discovery challenges our current understanding of the universe. The Big Ring is far too large and structured to be explained easily by the known process of baryon acoustic oscillations. Those pressure waves in the early universe could create a large-scale distribution of galaxies, but they would form roughly spherical shells, not stretched-out rings, and certainly not on this massive of a scale. If the data continues to hold up, it might mean that our assumptions about large-scale uniformity need to be reconsidered. Neither of these enormous structures can be easily explained by our present models, says Alexia Lopez, the astronomer who discovered them. Their immense sizes and unusual shapes are almost certainly telling us something important. But what exactly? One idea is that these superstructures could simply be statistical coincidences, random clusters that happen to grow larger than expected. But the odds of finding not just one, but several of these huge formations, including the Sloan Great Wall, the South Pole Wall, and the massive quasar groups, are becoming increasingly small. Another possibility is that they point toward new physics or different conditions in the early universe. Perhaps some unknown process that took place shortly after the Big Bang shaped these megastructures, extending beyond what standard inflationary cosmology can explain. For example, cosmic strings, hypothetical ultra-thin defects in space-time left over from the Big Bang, could have influenced how matter spread on vast scales. If they exist, though still theoretical, they represent one possible explanation for such anomalies. A more radical idea, proposed by the physicist Sir Roger Penrose, goes even further. He suggests that these massive structures could be remnants of a universe that existed before the Big Bang. In Penrose's model, called conformal cyclic cosmology, the Big Bang wasn't the beginning, but rather a transition between cosmic aeons. If that's true, the traces of a previous universe could still be visible in ours. Penrose even proposed that ring-like marks in the cosmic microwave background might be remnants of gravitational waves from the collapse of a previous universe. While most cosmologists remain doubtful of this idea, the presence of such patterns forces us to admit that we may not completely understand the physics of the early universe. Let's recap what we know so far. The Big Bang represents the beginning of the universe's expansion. For the first few billion years, this expansion slowed because of gravity. But in 1998, scientists made a surprising discovery. The expansion was speeding up instead of slowing down. Something unknown, later called dark energy, was pushing the universe outward, overcoming gravity on large scales. Even today, dark energy remains one of the biggest mysteries in cosmology. We know it makes up roughly 60% of everything in the universe, and acts like a form of anti-gravity, driving galaxies further apart. For years, the simplest explanation has been that dark energy is a cosmological constant, a fixed property of space itself, possibly related to vacuum energy. In our current model, known as the lambda CDM model, where lambda represents dark energy, this force stays constant over time, leading to an endless and accelerating expansion of the universe. However, new data suggests that this explanation might not be entirely correct. Observations from the Dark Energy Spectroscopic Instrument, DESI, which has studied millions of galaxies and quasars, shows that dark energy's effect may have changed over billions of years. In early 2025, researchers analyzing 3 years of DESI data found evidence that dark energy may have weakened with time. In other words, instead of providing a constant outward push, its repulsive strength could be slowly fading. According to Dr. Arjun from NSF's Noir Lab, the DESI findings suggest that dark energy might be evolving. If this turns out to be true, it would significantly change our understanding of the universe. It could mean that the cosmic acceleration we observe today will not last forever. As one researcher explained, the force driving the expansion could be losing strength or decaying. This raises important questions about the universe's future. Could the acceleration eventually slow down or even reverse? Might gravity regain control, causing the expansion to halt or collapse in the distant future? We simply don't know yet. But it's becoming clear that the long-standing idea of constant dark energy is now being questioned. Just like dark energy, another invisible yet essential component of the cosmos is under close study: dark matter. Dark matter, which can only be detected through its gravitational effects, is believed to form the framework for galaxies and galaxy clusters. It plays a crucial role in computer simulations that explain how cosmic structures form. Without dark matter, it would be difficult to understand how galaxies developed so quickly after the Big Bang. Despite decades of research, no one's directly detected dark matter particles, and their true nature is still a mystery. The ongoing challenge has led some physicists to consider bold new ideas that could remove the need for both dark matter and dark energy altogether. One such proposal came from Dr. Richard Liu, a physics professor who in 2015 introduced a new model questioning the idea of a single Big Bang. According to Liu, the universe's expansion and structure might not be the result of one event, but rather several smaller mini-bangs or temporary singularities that occurred in sequence. Instead of one initial explosion followed by continuous expansion powered by dark energy, Liu suggests that bursts of matter and energy entered the universe at different times. These brief but powerful episodes could explain what we observe today, replacing both dark energy and dark matter with sudden creation events. During each burst, matter and energy would spread evenly across the cosmos before the singularity vanished. These events would be so rare and brief that we wouldn't observe them directly. They would appear as cosmic flickers that slightly alter the expansion rate and lead to the formation of new structures. Between bursts, the universe would expand steadily without the need for mysterious dark energy. This idea stands out because it revives elements of the older steady states theory, which proposed that matter is constantly being created. However, Liu's version avoids breaking the law of energy conservation. The traditional steady-state model was rejected because it required continuous creation from nothing, which isn't physically possible. In contrast, Liu's transient singularities appear and disappear so quickly that they bypass such issues. For a fleeting moment, each burst injects energy and mass throughout the universe and then vanishes. Interestingly, this can be described in a way that fits within known physics, though it stretches the limits of current understanding. These temporary singularities would also generate a form of negative pressure, similar to what dark energy produces. Essentially, each burst could trigger a brief period of accelerated expansion, explaining the dark energy effect during that time, while also creating the density variations needed for galaxy formation, the role often attributed to dark matter. Liu's paper suggests that the original Big Bang might have been simply the first of many such bursts, the one that started the cycle. In the standard cosmological model, there was only one creation event. In Liu's model, there are many. It's a major shift from conventional thinking and, as of now, remains speculative. How could we test this idea? Scientists propose searching for specific patterns in astronomical data. For example, tiny irregularities in the redshift distance relationship of distant galaxies. If the universe truly experienced multiple bursts of expansion, faraway galaxies might not fit neatly along the smooth curve predicted by a model with constant dark energy. Instead, there could be small discontinuities marking those ancient bursts. Whether or not this specific theory is ever proven, its very proposal draws attention to an important point. The Big Bang model, despite its major success, still contains deep mysteries, and solving them might mean going beyond the idea of a single cosmic beginning. But let's return to the central question. What if the Big Bang wasn't truly the start of everything? Modern cosmology actually allows for that possibility. We've already seen Penrose's concept of a cyclic universe, where our Big Bang is just the latest in an endless sequence of universes, each emerging from the remains of the one before it. In this model, far into the future, when the universe has expanded endlessly and all matter has decayed, it enters an almost empty state that curiously mirrors the conditions of a new Big Bang, and at that point, a new aeon could begin. It's an ingenious attempt to connect the end of one universe with the birth of another, though it hasn't gained full acceptance among scientists. Penrose even claimed to have found concentric circular patterns in the cosmic microwave background, features he interpreted as evidence of gravitational events that occurred before our Big Bang. However, most researchers remain skeptical of this claim. Still, the idea of a universe that renews itself in cycles is far from new. Ancient philosophers also imagined an eternal cosmos that repeats endlessly. Some modern theories, like the ekpyrotic model involving the collision of brains in higher dimensions, share a similar idea. Instead of a single beginning, there's a cosmic bounce. These models suggest that something indeed existed before our universe, another one that came before in an endless cycle. Another perspective suggests that time itself began with the Big Bang, meaning that the question of what came before might not even make sense. It's like asking what lies north of the North Pole. For a long time, this was the standard interpretation of general relativity. At time zero, the equation simply stopped working, so one could say that time itself did not exist prior to that point. However, quantum physics challenges that boundary. Some quantum gravity theories, such as loop quantum cosmology, propose that the Big Bang might have been a big bounce, where a previous universe collapsed and then expanded again into ours. In these scenarios, time doesn't end, it continues through the bounce. So there was indeed a before, the universe that existed before the rebound, parts of which might still leave traces in our present cosmos. This suggests that the Big Bang may not have been a creation from nothing, but rather a transition between two cosmic phases. If dark energy is truly changing over time and could one day reverse, as some DESI results hint, then our universe might eventually stop expanding and begin contracting. That could lead to a big crunch, an event that might trigger another explosion, starting the cycle once more. Of course, this remains speculation, but it demonstrates that the question of what happened before or after the Big Bang is not just philosophical, it's an active area of scientific research. Current evidence shows a universe that the Big Bang theory describes remarkably well, yet one that still contains surprises challenging our understanding. About 13.8 billion years ago, the entire cosmos was a tiny, hot, dense ball of energy that suddenly exploded, according to the Big Bang theory, which first emerged in the 1920s. Over the decades, this theory has been refined, particularly in the 1980s, when many cosmologists proposed that the universe experienced a brief period of rapid expansion called inflation in its earliest moments. This inflation, caused by a peculiar form of high-energy matter that reversed gravity, expanded the universe exponentially, growing it by a factor of 1,000,000 billion billion in less than a billionth of a billionth of a billionth of a second. Inflation explains why the universe appears smooth and homogeneous on large scales. However, this raises questions about what, if anything, came before the Big Bang, and why the universe began as it did. Some see this as leaving room for the idea of a divine creator, a being beyond time and space. Others suggest that asking what existed before the universe might be as nonsensical as asking what's north of the North Pole. Although effects within the universe have causes, the universe as a whole may not have one or need one. However, this answer isn't very satisfying, and physicist Brian Cox suggests some possible scenarios. If the universe is eternal, it might not have had a beginning. If it's eternal, what role would a creator have? He suggests that something massive and terrifying existed before the Big Bang.
It's interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang, if you define the Big Bang as the hot, dense phase from which the universe appeared to sort of burst forth 13.8 billion years ago. And that phase is called inflation. So what we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe, 350 billion galaxies in it, in less than a millionths of a second. So very rapid, exponentially fast expansion. And when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which we are made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stopped the inflation? How long did the inflation go on for?
And the answer to that is we're not sure. We don't know.
Imagine that the universe we observe is just a drop in the cosmic ocean. Beyond what we can see, there could be more space, stars, galaxies, and everything else, perhaps extending billions of light years further than we will ever access. As vast as the unobservable universe is, there are likely countless more universes just like it, varying in size and age, spread throughout an even larger space-time. As these universes expand rapidly, the space-time containing them expands even more quickly, driving them apart and ensuring they never meet. This concept, known as the multiverse, may sound like fantasy, but if current scientific understanding is correct, it is a valid idea and an unavoidable consequence of our fundamental flaws. One example of these multiverse theories is the inflationary multiverse, which describes what occurred before the Big Bang. The concept of the multiverse is rooted in the physics used to describe our observable universe. When we look into the sky, we see stars and galaxies forming a vast cosmic web. As we look further away in space, we also look further back in time. Distant galaxies are younger and less evolved, with stars containing fewer heavy elements. These galaxies appear smaller due to fewer mergers, and there are more spiral galaxies compared to ellipticals, which develop from mergers over time. At the edge of our observable universe, we encounter the earliest stars and a region of darkness, where only the residual glow from the Big Bang is visible. However, the Big Bang, which occurred about 13.8 billion years ago, marked the beginning of our observable universe, not the inception of space and time itself. Before this, there was a period known as cosmic inflation, during which space expanded exponentially and was filled with energy inherent to space-time. Cosmic inflation is a theory that advanced beyond the Big Bang model by maintaining its successes and incorporating modern cosmology. It addressed several issues that the Big Bang theory could not, such as the uniform temperature of the universe, its spatial flatness, and the absence of high-energy relics like magnetic monopoles. Cosmic inflation also made several new predictions, most of which have been confirmed through observations. However, one consequence of inflation, the multiverse, remains uncertain. Inflation causes space to expand at an exponential rate, but whether the multiverse can be confirmed remains unknown. This process takes the state before the hot Big Bang and expands it significantly. This expansion helps explain the uniformity and vastness of the universe. When inflation concludes, matter and radiation fill the universe, which we observe as the hot Big Bang. However, things get complex when considering that for inflation to end, the quantum field responsible must transition from a high-energy unstable state to a low-energy stable state. This transition, moving into a lower-energy valley, brings inflation to an end and initiates the hot Big Bang. Moreover, the field driving inflation, like all fields governed by physical laws, must inherently be a quantum field. Like all quantum fields, it's described by a wave function that represents the probability of the wave spreading over time. If the field rolls slowly down the hill, the quantum spreading of the wave function will outpace the roll. This means that inflation can continue for a long time, potentially leading to more Big Bang events as time progresses. During inflation, space expands exponentially, creating more regions of space continuously. In some regions, inflation will end as the field rolls into a valley, but in others it'll persist, leading to an ever-increasing amount of space around regions where inflation has stopped. The rate of inflation is much faster than the maximum expansion rate of a matter and energy-filled universe, causing the inflating regions to eventually dominate all of space. According to the mechanisms that explain sufficient inflation to create our observable universe, there are many regions of space beyond our own where inflation has ended, and others where it continues. This leads to the concept known as eternal inflation. In regions where inflation ends, we observe a hot Big Bang that leads to a universe similar to our own. In areas where inflation persists, it creates more inflating space, resulting in regions with their own big bangs, which are causally disconnected from ours, and regions that continue to inflate. This idea of a vast universe, far larger than the part we can observe, constantly generating new regions through inflation, forms the basis of the multiverse concept. However, it's important to note that the multiverse itself is not a scientific theory with predictions for observable phenomena within our own universe. The multiverse is a theoretical prediction based on our current understanding of the laws of physics. It might be an inevitable outcome of these laws. In an inflationary universe governed by quantum physics, a multiverse could naturally arise. However, if our understanding of the pre-Big Bang state or inflation is incorrect, the existence of a multiverse might not follow. Nonetheless, if our current theories are accurate, the idea of an eternally inflating state, where countless pocket universes are continuously created and separated, directly results from these theories. The multiverse concept could extend beyond physics, potentially representing a new form of metaphysics. It offers insights into the limitations of what our universe can reveal. There is information we need, but may never obtain to make this testable science. Until then, we can predict but not verify or refute the idea that our universe is part of a larger multiverse. Although many aspects remain unknown, there are ways to approach the concept of the multiverse, starting with the universe itself. By definition, the universe encompasses everything. It includes all of physical existence. If it exists, it's part of the universe. Even with this broad definition, we can begin to explore the possibility of other universes. Our approach involves recognizing that the universe has a finite age and that light travels at a limited speed, setting a boundary on our observational capabilities. This boundary extends about 45 billion light-years away. However, this explanation provides only a limited view of the multiverse. There is more to the universe than what we can observe, suggesting that there are additional stars, galaxies, and possibly even intelligent beings beyond our reach. These entities exist in the universe, but are separate from our own world. In the concept of the multiverse, our universe is just one among an infinite series of universes. Imagine a giant foam, similar to the bubbles in a bubble bath. The multiverse represents this foam, continuously expanding and forming new bubbles, each representing a separate cosmos. These bubble universes all exist within the same space-time framework. Point in any direction, and past an immense distance, there's another universe, and beyond that, yet another. If this process of expansion never ceases, then the multiverse would contain an infinite number of universes. Each of those universes might have ended their local inflation in a similar way, but it's also possible that as each universe separated, it developed a new set of physics, including different forces and particles. Some of these universes might closely resemble our own, while others could be failures, filled only with void. Some may be far stranger than we can imagine, and some might be exact replicas of ours. If, hypothetically, there are only a finite number of ways to arrange all the particles in a universe, then with an infinite number of universes, repeated copies are likely. This means that not only could there be another universe in some random direction, but following that line far enough might lead to a duplicate of you doing exactly the same thing as you are right now. This idea is fascinating but challenging to test. The issue with the multiverse theory is that the bubbles representing different universes are completely isolated from one another. They exist separately, so traveling to a neighboring universe is not feasible with current technology. However, there might have been cosmic events in the distant past that could offer some insight. When our universe was young and recently separated from a larger inflation-driven expansion, it's possible that another bubble universe was nucleating nearby. If that were the case, our universes might have briefly intersected before being pushed apart permanently. While the likelihood of such an occurrence is extremely low, it's not impossible, which provides a potential method for testing the multiverse theory. Unfortunately, no observations so far have shown evidence of such a collision, which doesn't disprove the multiverse, but also doesn't provide supporting evidence. The only remaining basis we have is our theoretical understanding of the early universe, which remains incomplete. We only have a vague idea of what inflation entails, and many aspects of it, such as its driving force, the energy levels involved, and why it ended in our universe, are still unknown. Additionally, it's unclear whether inflation inevitably leads to a multiverse, or if we might be misinterpreting our own calculations. Despite ongoing debates among physicists, the concept makes for an intriguing story. Aside from the multiverse theory, there are alternatives like the cyclic universe model. This model proposes that our current observable universe is part of a sequence of universes. According to this view, our universe is expanding due to the Hubble parameter, and if this parameter remains constant, expansion will continue indefinitely. However, if the Hubble parameter is cyclical, the universe will eventually begin contracting, leading to a new hot, dense state, a new Big Bang for a new universe. In this model, the universe has no definitive beginning. It is eternal. However, the cyclic universe model has its own set of challenges. One significant issue is the problem of entropy. Entropy measures disorder within a system, and according to thermodynamic laws, can only increase. In a simple cyclic universe model, the entropy of any universe should be slightly higher than that of its parent universe. This implies that if universes cycle infinitely into the past, the current universe would have infinite entropy, which is not the case. Therefore, there must have been an initial universe with low entropy, bringing us back to the starting point. A potential solution involves introducing an overall scale factor for the universe. If this scale factor increases with each universe, the entropy issue can be resolved. This scale factor is conformally invariant, meaning it does not alter the appearance of the universe. Each universe might be twice as large as the previous one, but everything within it scales proportionally. For example, if everyone's income and the cost of everything doubles, there's no real change. This conformally invariant scale factor allows for a cyclic universe without requiring a specific beginning. The idea that each universe has a cause and that it's turtles all the way down has been challenged by a recent study. The research team examined the mathematical framework of cyclic universe models in general relativity and discovered that all such models are geodesically past incomplete. This means that according to general relativity, it's impossible to trace our universe back through an infinite cycle of previous universes. While there may have been many universes before ours, there must have been a first universe. The cyclic universe model can suggest a cause for our universe, but only shifts the question of origins further back. Even if our universe wasn't the first, some universe was. The study's findings do not apply to conformal cyclic cosmology proposed by Roger Penrose, where each universe's scale is infinitely larger than the previous one. The authors intend to explore this model next, which will be discussed in a further study. Another approach in theoretical physics is M-theory, which aims to unify various string theories and supergravity into a single, coherent framework. It is considered a leading candidate for a theory of everything, which seeks to describe all fundamental forces and particles in the universe within one comprehensive theory. M-theory has been interpreted in several ways, including as membranes, magic, mystery, and matrix, reflecting its complex and somewhat ambiguous nature. Its implications extend to cosmology, the study of the universe's origin, evolution, and ultimate fate. One major contribution of M-theory is the concept of the multiverse, suggesting that our universe might just be one of many, each with its own distinct physical laws and constants. These universes could be connected through higher dimensional spaces, and might interact in ways that could potentially be observed, such as through gravitational waves or cosmic phenomena. An interesting aspect of M-theory in cosmology is the concept of brain-world scenarios. In these models, our four-dimensional universe is seen as a three-brain within a higher dimensional space. This view offers potential explanations for various cosmological phenomena, such as dark matter, dark energy, the hierarchy problem, and the initial conditions of the Big Bang. However, M-theory is not yet fully understood, with many of its mathematical formulations and predictions still speculative. One major challenge is the lack of direct experimental evidence, as the energy levels where M-theory's effects would become observable are beyond the reach of current particle accelerators. In the end, we must acknowledge our ignorance about the true beginning of the universe. Even if we consider the idea of an eternal multiverse with no definitive start, we still don't understand why there's something rather than nothing. The complexity of the universe exceeds our complete comprehension. Space is filled with celestial phenomena, some of which are incredibly beautiful, while others are intimidating. Our fear often comes from our limited grasp of these cosmic events. Here are 7 unsettling cosmic entities or phenomena. Dark matter. Dark matter is a mysterious form of matter that constitutes about 30% of the observable universe's matter energy. Despite its significant presence, little is known about it. First suggested by Swiss astronomer Fritz Zwicky in the 1930s, dark matter gained broader recognition in the 1970s when Vera Rubin provided strong evidence through her studies of galaxy rotation. What makes dark matter so perplexing is that it neither emits, absorbs, nor reflects light, making it invisible to direct observation. We infer its presence only through its gravitational effects. Dark matter influences galaxy cluster formation, affects galaxy rotation speeds, and causes gravitational lensing. Several potential candidates for dark matter particles have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. WIMPs are currently the leading candidates due to their weak interaction with regular matter and their potential for detection through rare collisions. The unknown nature of such a large portion of the universe's mass is both unsettling and intriguing, driving the ongoing search for dark matter. Rogue black holes. Black holes form from dying stars that undergo gravitational collapse after they've used up their nuclear fuel. They have the strongest gravitational pull of any objects in the universe. While black holes can be found in various sizes and are often located at the centers of galaxies, not all are in these locations. Nothing can escape a black hole's gravitational pull, not even light. A particularly unsettling scenario is when a black hole roams through space independently, known as a rogue black hole. These rogue black holes are not bound to any galaxy and result from incomplete mergers between colliding galaxies. One of the few rogue black holes directly detected was observed in January 2022 using the Hubble Space Telescope. This black hole, named OGLE 2011 BLG0462, is 5,000 light-years away and has a mass about 7.1 times that of the Sun, moving at a speed of around 45 kilometers per second. If a rogue black hole were to approach our solar system, its gravitational pull could disrupt all celestial objects, including the Sun and planets. However, given the vast distances between stars and the rarity of rogue black holes, such an event is extremely unlikely. Zombie stars. Supernovas are massive explosions that occur at the end of a star's life, releasing enough energy to temporarily outshine entire galaxies. They often leave behind remnants like neutron stars or black holes. Among the various types of supernovas, type 1a is particularly interesting. These events occur in binary systems where a white dwarf accumulates matter from its companion, leading to a catastrophic explosion with consistent luminosity. Scientists have identified a subtype called type 1ax supernovae, which have lower luminosity and ejection velocity than type 1a. The remnant of this subtype is a zombie star. Supernovas are rare events, making these stars hard to observe. A significant achievement was the observation of supernova SN2012Z, a type 1ax supernova, and the first identified star system observed before it went supernova. Historical records show that supernova SN1181 was observed in 1181 AD by Chinese and Japanese astronomers. Modern astronomers, including Dana-Padshek, later linked SN 1181 to the nebula P30 and the central star IRAS 00500 plus 6713, now confirmed as a zombie star. IRAS 00500 plus 6713 is the only known zombie star in the Milky Way. The limited knowledge about zombie stars adds to their eerie fascination, along with their unconventional characteristics and implications for stellar evolution, though the name is more evocative than descriptive. Galaxies without dark matter. Dark matter is generally considered the invisible glue that holds galaxies together, but scientists have observed galaxies with much less dark matter than expected. DF2 and DF4 are examples of galaxies with very low velocity dispersions, indicating little or no dark matter. This finding challenges conventional theories of galaxy formation and evolution, which suggest that galaxies form within vast halos of dark matter. One study proposes that these galaxies formed due to high-velocity collisions of gas-rich galaxies, similar to the collisions that created the Bullet Cluster, but on a smaller scale. In this scenario, gas separates from dark matter during the collision, and subsequent star formation creates dark matter-free galaxies. The Hubble telescope has been used to measure these galaxies accurately, but the missing dark matter remains unexplained. This raises the question, if not dark matter, what holds these galaxies together? Boomerang Nebula. The Eastern Antarctic Plateau in Antarctica is the coldest place on Earth, but it's still 3 times warmer than the universe's Boomerang Nebula, one of the most frigid places in space. Also called the Bowtie Nebula for its shape, it's located in the constellation Centaurus and is the coldest known place in the universe, with a temperature of 1 Kelvin, or minus 272.15 degrees Celsius. The Boomerang Nebula is a protoplanetary nebula, representing a star system transitioning to the planetary nebula phase, the final stage of stellar evolution. Scientists believe the nebula's central star is a dying red giant, emitting gas that forms the nebula. This gas outflow creates an hourglass shape illuminated by starlight. In 1995, astronomers using the ESO submillimeter telescope in Chile measured its temperature as 1 degree above absolute zero, colder than the background radiation from the Big Bang. The Boomerang Nebula's extreme cold challenges scientists' understanding of energy balance in space, as it raises questions about the mechanisms and processes at play. Strange matter is another type of matter made of strange quarks, fundamental particles. Hypothesized to exist in extreme conditions and environments like the cores of neutron stars, or as isolated droplets called strangelets, it ranges in size from femtometers to kilometers. Scientists propose that strange matter forms when nuclear matter is compressed beyond a critical density, dissociating protons and neutrons into quarks. The strange matter hypothesis, also known as the Bodmer-Witten assumption, suggests quark matter is the true ground state of all matter, making it more stable than ordinary nuclear matter. Researchers are seeking observable signs to determine if neutron stars contain quark matter, which would classify them as hybrid stars. While strange matter is a compelling theoretical concept, it remains unproven, with no physical evidence yet supporting its existence. Near-Earth objects. The solar system contains various celestial objects like asteroids and comets, some of which can approach Earth during its orbit. These objects, known as near-Earth objects, NEOs, are small solar system objects that can come close to Earth when their orbits intersect or come near Earth's orbit. Scientists have discovered 23 comets passing within 0.1 astronomical units, AU, or 149.6 million kilometers of Earth. Recent examples include asteroid 2020 VT4 and 2020 AP2. The potential impact of these objects on Earth is significant, as they could enter the atmosphere and cause damage, such as creating tsunami waves or craters. Scientists have sent spacecraft to NEOs to collect samples to study their composition and understand their origin better. Initiatives like Space Guard surveys and the Planetary Defense Coordination Office have been established to detect, track, and assess NEOs. This allows for early warnings and the development of strategies for potential deflection or mitigation. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode.